Good evening, everyone, and welcome to this final event of the night, we think, of the Cryosphere Pavilion. We'd like to give a special thanks to those of you who are watching at the Pavilion hubs in Geneva and Stockholm. There will be a chance to ask questions as we move through these presentations, but I think we'll hold them all until the end. My name is Pam Pearson. I'm the director of the International Cryosphere Climate Initiative. Welcome to Glasgow. It's a very busy evening here. There is a stock-taking session going on in plenary, which we appreciate those of you who are here, being here to listen to this science and its relationship to policy. But a lot happening in the negotiations, and I'll touch on that towards the end of this event. This is a presentation that is essentially a summary of the Toblerones that you see here. We have been giving this presentation, and by we, I mean people who work with ICCI, but especially the scientists with ICCI, virtually. This is something we developed because of COVID. Tonight is a bit of a treat for us because many of the scientists who have participated in these virtual events, or at least a few of them, are here. And so really for the first time, we're going to be giving it switching off with each other in person rather than on Zoom. So these are the presenters, or in some cases, I'll be standing in for the presenters. We're going to begin with ice sheets and sea level rise. You see that Tobler over there. We call these the Toblerones. They're three-sided, of course. Glaciers and snow will be Dr. Heidi Silvestre. Arctic sea ice, Julianne Strove, NSIDC, University of Manitoba, University College London, was unable to be here, and so I will give her section. Same for Helen Findlay of Plymouth Marine Laboratory here in the UK. Gustav Hugelius from Bolin Centre, he was here last week, but not here tonight. And Yori Rogali, unfortunately, needed to run to a 6 p.m. meeting. So we'll give his presentation as well. But we have at least three of us here to give it in person, as I said, for the first time, and I'll round off. So I'll turn it over to Julie Brigham-Greta, University of Massachusetts Amherst, and many other wonderful titles.
Thank you, Pam, and welcome everyone this evening. So I'm a climate scientist and I do paleoclimate, particularly sea level and ice sheets, the relationship between sea level and ice sheets. And one of the reasons why, of course, we need to keep the Earth below 1.5 degrees is because the paleoclimate history of our planet, particularly looking at past sea levels, tells us what sea level does when ice sheets melt and how high does it go when different ice sheets of different sizes or combinations of ice sheets do collapse during glacial, interglacial times. And so we can use the elevation of these sea levels and the conditions to then look at what the conditions might be like as we go forward. And as you can see here we're talking about at 1 degree, we're already facing at least 2 to 3 meters of sea level rise are baked into our system. Sea level is rising, and that is not reversible. I can't emphasize that enough. We're not going to be able to grow these ice sheets back anytime soon. If we go back to what we call the Eemian, it was in the glacial interglacial cycles, the last time it was as warm as it is today for about 10,000 years. We call that the Eemian. And during that period, sea level was in the range of 6 to 9 meters above present. And that was at a temperature of about 1.5 degrees. So again, we're already kind of there or approaching it. And so we're already baking in to the system serious sea level rise in our coming decades and centuries, because we've already got that baked into the system. And so what melted, we think, working with ice sheet scientists, that at least 2 to 3 meters of that total came from the melt of Greenland. and the rest of it probably came from the West Antarctic ice sheet, that for the most part. But you can also see that if we go back in time, even to the Pliocene, about 3 million years ago, when there was, at that time, no West Antarctic ice sheet, and the Greenland ice sheet was much, much smaller, we had sea levels in the range of about 20 meters. And this has actually been several papers that have come out in the last couple of years that really make that number pretty strong, about 20 meters of sea level. So that means that's a lot of ice. And of course, if we go anything higher than that, we're really facing approaching an ice-free conditions. And the other thing, so the question is not how much, but how fast and how much we're committed to this. Of course, as I said, it's not reversible. And we know from an event about 14,000 years ago that ice sheets of these large size can collapse quickly. And there's a period of time at about 14,000 years ago when sea level rose dramatically in just about 400 or 500 years. So we know that the ice sheets are capable of this type of rapid collapse. Here is an idea of what the Greenland ice sheet may look like by 2023. So this fits with predictions, particularly in areas of heavy melt that we see today, with forecasting out into the future what these ice sheets will do. Will they melt dramatically fast, like in a few years? No. In fact, it's not part of this presentation, but papers have come out recently to suggest that business as usual, RCP 8.5, the entire Greenland ice sheet could be gone in less than 1,000 years. Okay, so by the year 3000, that's okay. So that's not 3,000 years from now, but by the year 3000. So we're getting better at trying to predict what these temperatures will do. So, of course, part of the sea level rise is kind of going to be coming from Antarctica. There's a lot of research being done, particularly on ice sheet stability. We can forecast here in this paper possibly as much as 30 to 40 centimeters, maybe a half a meter from Antarctica by 2100. And after that time, particularly if we don't do anything about CO2, if we stay business as usual, sometime around 2060, by that time we're bifurcating away from and driving the system of many of these ice sheets, particularly the ice shelves, that may put us on a path to more rapid high sea level because of the loss of the buttressing power of the ice shelf. So this is why now, what we do now, there's a role for policy to determine which track we're on with these different pathways. I mentioned these ice shelves. All of these areas in red that are on this particular figure, they are floating ice. They can be as much as 400 meters thick, but they're floating, but they're buttressing, they're holding back the ice. And if they collapse, they then release all of the ice behind. We've seen this happen more recently up the Antarctic Peninsula. 7 of the 10 ice shelves in that area have all collapsed in the last few decades. And we can see, particularly with remote sensing, very rapid increase in the flow of the ice that's on land into the sea, which of course is going to rise sea level. And so current concerns are in that red box in the Pine Island Thwaites Glacier region, where we've seen tremendous melt of the ice shelves there, both from the bottom, from warm water from the circumantarctic current getting up under those shelves in ways that we had not ever observed before, as well as melt happening on the surface. So this part of West Antarctica is warming up, whereas other parts of Antarctica, you might argue it's not feeling a thing about global warming, but this area is. So some people have suggested that we've already reached the tipping point, that we've already at a point of no return with the collapse of some of these ice shelves. So what are the consequences for sea level then? Well, let's think about that. This is a a website from Climate Central. There's a poster from them here on the back of the wall where it takes different coastal cities and increases sea level. You can actually go into this website yourself and play around with a toggle and look for your favorite coastal area and see what happens with a meter or 2 meters. So here is a change in elevation of sea level by about 3 meters. And so you can pick out your favorite place here in the UK. Here it is at 20 meters. This would be a Pliocene shoreline from 3 million years ago. And here we go London. And here we come into, we can increase here at 10 meters in London, 20 meters in London. And then of course, we can come up here to Glasgow. Here's Glasgow at 20 meters. So that's a Pliocene world. And I just want to mention, in the Pliocene, the atmosphere was already at over 400 parts per mil CO2. So we're in a Pliocene atmosphere right now already. We're driving the planet toward a Pliocene. So my last slide is just to show you again what happens now directs and has a very important role for policy in terms of the trajectory we're going to be on for sea level. So I think I'll leave it at that and go on to the next slide.
Well, at this COP, flexibility is the name of the game. The presenter for this is over there briefing the Swiss Minister of Environment. I'm not going to pull her away from that. Instead, I am going to, but she's a treat to listen to, so I'm simply going to scroll ahead and then we'll come back to her once she's done. Because I know the Swiss Minister is very busy, and so it's certainly not going to take the period of time of the rest of this event. So if you will bear with us. Okay. This is Arctic sea ice, and this is a presentation that Julianne Strove or Dirk Knotts or Walt Meyer normally would give. And of course, there's been a huge change in the extent of Arctic sea ice already at today's 1.2 degrees. Loss of about 40%, but even more so, there's been a thickness loss in Arctic sea ice. That's in some ways the most important, because with that volume of ice gone, a lot of species are very dependent on it. And with the release of AR6, the ice community, the sea ice community, you might have noticed that there wasn't a whole lot in the summary for policymakers if you read that. That's because from their point of view, this is what I was told by them, that Arctic sea ice is essentially already tipped into a new state. It is very thin, and their only real conclusion in the SPM was simply that sometime between now and 2050, no matter what emission scenario we follow, there will be at least one ice-free summer. And with that ice-free summer will be, you know, a very large change in the ecosystem, in its ability to bounce back. This is also an important aspect of Arctic sea ice loss. It's a very busy slide, of course, but what you see here going from left to right, 1980 to 2020, are periods of more or less ice than the average between 1981 and 2010. And as you can see, for all months of the year, we have less sea ice. So there's a lot of focus every year on the September minimum, when the sea ice normally reaches its lowest minimum extent. But part of the news is that year round, it's actually setting records. Last year, although the actual minimum was not a record, sea ice actually was at record minimums almost every other month of the year, and then it had a period of recovery. Very straight tracking with CO2 emissions and temperature. And this is an interesting slide. I love the way Julianne did this. I'm going to step over into here now. But what you see here are the periods in the different months of the year on the left where it's ice covered and ice free. The threshold of temperature for no summer sea ice at every single year is about 1.7 degrees. We'll have occasional ice-free years, even at 1.5 degrees, but by 1.7, every September, there will be a few days or weeks of ice-free conditions in the Arctic. And then if it gets warmer still, then there will be longer periods where the Arctic Ocean is essentially ice-free. That's going to have implications for all sorts of portions of the Earth system. It affects Greenland ice sheet melt. It affects the degree of permafrost melt, and then just overall albedo of the cooling of the Earth. But as you can see here, it just grows and grows. And if we're at 3 degrees, then you're looking at a really long period when the Arctic is ice-free. And again, the longer that gets, the more extreme conditions as a result of that. And we're really not sure because we've never lived as humans in a world that has an ice-free Arctic, especially for that much of the year. And in model projections, these are the new SSPs. In other words, what we call over here very low emissions, intermediate and high. You see this decrease, but in September, on the left-hand graph, a lot of that decrease has already occurred. What we see in the future with high emissions is you see an equally extreme decrease than in March, which is the maximum for summer sea ice. And volume is going down just as much, or if not more, than area. And this is important for the Arctic ecosystem because you need to think of sea ice. It's not just, ice sitting there. It's very thick, or at least it has been. It's not so long ago that a fairly substantial portion of Arctic sea ice was more than 10 years old. So this was really, really thick ice. It was like a coral reef would be in the rest of the world. Organisms live there. They depend on it. And without that, the ecosystem undergoes a basic state change, which has already occurred. And this is just a representation of one potential implication. There was a side event focused on this of Arctic sea ice loss, where you have a much weaker jet stream. The winds, the polar vortex, as people like to call it, are able to break out of the Arctic, and you get cold periods that last for a period of time, or you get warm periods. You get very, very odd weather systems that are persistent over a long period of time that we have not seen, at least before, in the record. They're occurring more and more often. This is one of the more controversial aspects of sea ice loss. Very determined camps on both sides, but I think a lot of people have noticed weather differences. And a good way to think about this is Arctic sea ice is associated with the warming Arctic. These kinds of weather patterns are also associated with the warming Arctic. And the real message is that with the warmer Arctic, you get much less of a temperature gradient between the mid-latitudes, where Glasgow is, for example, and higher latitudes. And that's why you're getting these disturbances in the jet stream. And this is just some pictures of what's happened in the past. We move on now to the polar oceans. And there's a lot of attention at this COP to the oceans. Our focus is the polar oceans because they're different in many ways. They are warming faster than the other oceans. They are freshening at the same time because of the massive amounts of ice that are pouring off of Greenland and Antarctica, glaciers, as well as the ice sheets. And most importantly, perhaps in terms of a kind of permanent state change, is acidification. Colder waters absorb CO2 much more readily than warmer waters. And so they're acidifying much more quickly than the mid-latitude and the tropical oceans. So we're going to see acidification sooner. You could say that the polar oceans are performing an ecosystem service for the planet because they're one of the reasons that we're only at 420 parts per million now in terms of CO2 concentrations. By some estimates, the two polar oceans have absorbed about 60% of the CO2 that's been absorbed by the world's oceans. And this is the difference that we'll see between low and high emissions. So very low emissions is the lower globe. That's a 1.5 degrees C world staying about at 450 ppm or below, you're still seeing a fair amount of acidification over Canada and Siberia. But if we go into high emissions mode with very high levels of CO2, then we will end up with that world on the top, where in essence, shell building organisms will not be able to build and maintain their shells. Again, completely changing the ecosystem. And this is some shell damage that has been observed already. These pictures were taken from samples that were taken at about 410 ppm, around 2010. So we were seeing shell damage in some portions of the Arctic and Southern Oceans already at that point. And the key thing to think about is that acidification has a really long tail. I mean, everybody knows that CO2 lasts a long time in the atmosphere. It lasts even longer in the water. So for the ocean to buffer out and to come back up to the pH where it is today will take 50 to 70,000 years. Obviously, species can't wait around that long. And so this is really perhaps the longest threshold behavior that we see on the planet. And this is one of the reasons, as we say, why SRM, solar radiation management, as you heard earlier today, really is not a viable idea, because if, that might mask warming by reflecting back, some of the sun's rays back into space. But at the same time, CO2 continues rising and the oceans will continue absorbing it. And again, with that 50 to 70,000 year tail. So this shows that just, graphically, even by 2500, especially with very high emissions, you're just getting started to buffer that out. So this is an example then, practical terms for a lot of humans with cod. As I mentioned at the start of this section, you're getting a lot of freshening and warming. You're also getting incursion of invasive species from the south, right? The mid-latitude species are moving north. At the same time, you have warmer, fresher, more acidic waters moving from the south. And so what's happening to northern species like cod is that they're getting sandwiched between these bands, and there's eventually nowhere left for them to go. So unfortunately, we're probably seeing a situation where, especially with very high emissions, current wild living species such as cod and salmon are going to have a very hard time surviving in this new Arctic and northern oceans, places like the North Sea, the Barents Sea, because of the changes in the ecosystem. So I'm going to back up here and try to get, I saw that Heidi, I believe, was done. Amy, could you get Heidi over here while I back up to glaciers? I told them what you were doing, so we went ahead.
Hi, good evening, everyone. Thank you so much for your patience. Thank you for having me to talk about my favorite topic and the state of the Cryosphere report on the chapter that is focusing on mountain glaciers and snow. Perfect, thank you. So what about these mountain glaciers? We are tightly connected to all these mountain glaciers, whether they are in the Himalayas, in the Alps, all along the Andes. These glaciers play a very big importance on societies. They cover only a very small portion of the land masses on Earth. As you can see here, about 0.5% of all land ice is actually locked into these mountain glaciers. So here, I am actually ignoring the big ice sheets that are Greenland and Antarctica, only focusing on the mountain glaciers. These mountain glaciers, no matter how small they are, they were actually the largest contributors to sea level rise during the 20th century. So they are important. They play a capital role on sea level rise. We know that these mountain glaciers have a really big importance on the surrounding areas we find them. And for example, I'm from the French Alps, and we love our mountain glaciers. They have a big importance on our local economies. But also the meltwater coming from these mountain glaciers has an importance all along the rivers that are connected to these glaciers. So their importance, their influence is felt over hundreds and thousands of kilometers away from those mountain ranges. So why should we care? Why do we need to care so much about these mountain glaciers and also the snow falling on these beautiful mountain ranges? First of all, because of the water they provide. When the snow melts every spring, when glaciers lose mass every summer, they provide a lot of fresh water. And this fresh water can be used for drinking, can be used for sanitation, for irrigation, for the production of hydroelectricity. In my region, again, this water coming from the glaciers is also being used to cool down nuclear power plants. So that's very important. We do need the meltwater coming from these glaciers and also from the snow. We know that in the vulnerable regions, such as the tropics, for example, there are still glaciers in the tropics. The meltwater coming from the melting snow and ice is of huge importance during the dry seasons. So this is when the importance of the snowpack and of the glaciers is felt the most. We have some regions like in the US, for example, in the western US, western continental US, the melting snow also provides a very big resource of fresh water. And we know that when the snow melts more and more every year, when the glaciers lose more and more mass, it creates a range of consequences. It can create hazards, natural hazards. We have mountains that are being destabilized, slope instability that is felt very strongly. This also impacts local economies. If you think about recreational winter activities directly connected to the presence of snow and ice, they are suffering tremendously from the loss of snow and ice. When these mountain glaciers are lost, when they disappear, we also lose with them these incredible climate archives. You know, when we go to these mountains and collect ice cores, these ice cores tell us so much about past climate changes. When the glaciers are gone, we lose this very precious information. And finally, if you look at these mountain communities living around these glaciers, there is a lot of traditions, there is cultures that have been created around these glaciers that are being lost when the glaciers disappear. So now I will go through different regions and we're going to look at the future. Together, we're going to look at these projections all the way to the year 2300 and see what would happen to the glaciers in these different regions, depending on some of the decisions that are going to be made here at COP26. And the different scenarios are represented in different colors. In the blue color, this is the very low and low emission scenarios. In the orange color here, we're looking at the middle of the road scenario, and in red, this is business as usual. These are the high emission scenarios. And what you can see here on the diagram is the change in mass of the glaciers in these different regions. And here we're starting with the tropics, because there are still glaciers in the tropics. We call them tropical glaciers, and they're found in the northern Andes. We have glaciers left in Mexico, for example, glaciers in Colombia, Venezuela, Ecuador. We have glaciers in East Africa. We still have glaciers in Papua New Guinea. You might have not heard about them, but there's still some ice there. And we do know that for these tropical glaciers, an increase in temperature of +1 degree is already too much. Today, it is almost too late to save most of the tropical glaciers. If we follow even a 1.5 degree scenario, by the end of the century, only the glaciers at very high elevations, above 6,000 meters, will survive. All the glaciers in East Africa, Indonesia will be gone by the end of the century. So +1 is already too much for these glaciers. If we move to mid-latitude glaciers, so the beautiful glaciers of the French Alps are there. For example, we have Scandinavia, Caucasus, Western Canada, US, Southern Andes, and New Zealand. There, we start to see massive differences based on the different scenarios. If we were to follow business as usual, the high emission scenarios, we could lose most of these glaciers by the end of the century. But if you look at the scenarios in blue, look at the huge differences it would make to follow the low and very low emission scenarios. We could keep a very large proportion of these glaciers by the end of the century. And it's very important to look beyond the end of the century, because climate change obviously doesn't stop by 2300. And if we look at Central Europe, which is at the bottom right corner of the screen here, if we were to follow a 1.5 degree compatible scenario, not only we could keep about 40% of the ice mass we have in Central Europe today by 2100, but we could even get a slow regrowth of the glaciers if we look beyond 2100. So the differences are huge, especially if we're able to follow 1.5 degree compatible scenario. Now I'm going to move to the high altitude and high latitude glaciers. So the regions we're looking at are the Himalayas and also Arctic Canada. And here again, the differences between scenarios are absolutely massive. If we were to continue business as usual, if you look at the red curves, by 2300, we would lose so much of these glaciers. Especially look at the Himalayas, which are the diagrams on the left-hand side here. More than 1 billion people in the Himalayas, in India, in all the countries surrounding the Himalayas depend upon the water from the Himalayan glaciers. And if we were to follow business as usual, we could lose such a large portion of the glaciers in the Himalayas. But again, a 1.5 degree scenario is the only way. This is the only way we can keep as much of these glaciers as possible. And I will finish this presentation on this chapter on mountain glaciers and snow with the snow. Snow plays an even bigger role in bringing all these water resources to the people living around these mountain ranges and all along the rivers coming from these mountain ranges. We know today that the snowpack is suffering from the increase in temperature. The presence and the persistence of snow is changing all around the world, and also the precipitation patterns are being affected by climate change. We know that snow arrives later in the seasons, melts earlier. We know that the snowpack is thinning and the area covered by the snow is also being reduced more and more every year. And this snow is extremely important. When it falls on the ground, it acts like a blanket, protecting the soil underneath. We know that when the snow melts, it irrigates the soil, protecting the soil from being completely dry in the summer, protecting the soil from wildfires, for example. And of course, especially here in Scotland, we know that more than 600 people depend upon the snow for all the winter recreational activities. This employs 600 people in Scotland, so we still need very much the snow here in the country. And I think it shows the importance of the cryosphere in Scotland, in Glasgow, while we are assisting at the northernmost COP that is the closest to the Arctic, but also directly connected to this snowpack. Thank you. I think this was my last slide. Thank you very much. Oh, yeah, sure.
Don't go too far. Okay. So I'm going to click ahead to Gustav Hugelius, our final dynamic, which is permafrost. And Gustav is part of the International Permafrost Network. And this is a picture of a cliff formation, abrupt thaw, which is actually one of his areas of very, very active research. I'll get a bit back into that later. But basically what happens with permafrost when it thaws is that it releases carbon that's been stored for thousands of years, if not more. It releases it as CO2 under dry conditions, as methane under wet conditions. And so that's why you'll hear permafrost scientists talk about carbon release rather than trying to specify, because it's really very specific. And permafrost loss is ongoing. To date at 1.2 degrees C, this is the extent of near surface permafrost loss. So this is permafrost in the first few meters of the soil. And you can see how rapidly it's thawing. I'm going to go back just so you can see this again. So it's a really rapid loss. And this is important globally because it decreases the carbon budget available to humans. At 1.5 degrees C, you see that permafrost is still releasing a fairly substantial proportion of the carbon budget that is left. Permafrost emissions today are on the order of about the size of Japan, and they will increase the warmer it gets. At 2 degrees, there's a little bit more permafrost emissions, a lot more human emissions. There's actually quite a bit of a difference between 1.5 and 2. But the scale of emissions really depends on peak temperature, and even more so, and this is really difficult with permafrost, you can get a permafrost thaw in a heat wave. And we've seen lots of heat waves in the Arctic. And so this may actually be an underestimate of the degree of permafrost thaw we're going to see. But these permafrost emissions are really hard to capture in global models. And so even in AR6, in this new CIMIP6 models that are being used to project climate in the future and the behavior of the planet and the global climate system, these emissions are not actually included. They're sort of, there's a footnote, there's a bit of an estimate, but in terms of really, quantifying how much it's going to be, still it's the case that climate modelers at least don't want to include it. Permafrost modelers really think they should. And so it's an area of very active debate, let's say. But the other important thing with permafrost is that the emissions continue for centuries after the initial thaw. So I'll step over here in a second, but this is really important. This is, again, a matter of intergenerational justice, because you get a certain amount of emissions to 2100, but that permafrost continues emitting for a couple of 100 years. So if you look at the blue bar at 1.5 degrees C, you see the median emissions, but the multi-century is much higher. Same for 2 degrees C, and at 4 degrees C, it's even greater. In other words, what that's saying is that suppose we do reach net zero emissions by 2050. Permafrost is going to continue emitting for at least a couple of centuries after that. So in addition to the negative emissions that are in the models to keep temperature below 1.5 degrees C, we also have to have emissions to negative emissions to offset permafrost. And we're going to have to continue doing that for a couple of 100 years until the permafrost stabilizes, it's lost all of its carbon, and then, then we can truly have net zero. But net zero, in a sense, is not net zero until permafrost emissions are complete. So even if we bring temperatures down again, if this is permafrost that refreezes, it actually continues emitting very, very slowly. So we always try and end this with a bit of a moment of hope. And the 1.5 degree report, as well as we think Working Group 3, in AR6, which will come out in March of next year, 1.5 degrees still is within reach, but it does require rapid, far-reaching changes on an unprecedented scale. And it needs to be happening this decade, and that's why there's so much of an emphasis on now to 2030. That's why we've decided to release the State of the Cryosphere report every single year between now and 2030, both to take the pulse of the cryosphere and update on the latest science. And like these Toblerones do, if we did these today, we would say these optimistic NDCs, for example, that you see on the side that most of you are seeing towards me, optimistic NDCs, all of the pledges, you say everybody's going to say what they say they're going to say, even if they haven't put laws in place or any steps at all to make it happen. Peak now would be 1.8 degrees is what we're hearing in terms of the pledges that have come at this COP. But we have to pay attention to what countries are actually doing. Those are the other sides of those Toblers. And we need to see that happening about 50% globally by 2030. It's very important for policymakers, but even more so the general public, to understand if we do not decrease globally 50% emissions by 2030, then we will not reach net zero by 2050. It will no longer be physically or economically feasible to do so. That was in the 1.5 degree report. It was extremely clear. And so far, emissions continue to rise. So we're not there yet. And it's really important that governments understand the urgency. All stakeholders need to, but really this is a massive change, right? In energy, lands, transport and infrastructure, industry, all stakeholders need to be a part of that. But these are the kinds of things really that only large governments can do and make happen. And this is what those emissions reductions will look like. You have this very, very steep decline between 2020 and 2030 in the sectors where we know we're able to do this, which is primarily transport and energy. And then the net zero is those sectors that are a little bit more difficult, right? Industry, steel making, for example, other kinds of industries that are both carbon intensive, but steel, cement emits CO2 even in the process of making it happen. And also things like agriculture, where you have a lot of emissions, for example, from livestock. Those are the ones that we really don't know how to do right now, or we can't do at scale. That's between 2030 and 2050. And then negative emissions, carbon drawdown for the rest of the century to stay below 1.5 degrees. So are these changes still feasible? The special report said yes. Geophysically, in other words, the physical reality, yes. Environmentally feasible, we can do it and still protect the environment. Lots on nature-based solutions, for example, here. Technologically, we have the technology to make it happen. We really don't need new technology. And it's economically not just feasible, but advantageous, because we're not suffering the loss and damage that we will at temperatures above 1.5 degrees. What's left is institutional and social cultural feasibility, and that's up to us. That's what we need to decide at this COP and going forward over this next decade. So I'm going back a bit to Julie's presentation just to put us on this time scale, right? Glaciers, interglacials for a long time, and now we are really off the chart, and we need to bring it down again if we want to stay at safe levels. So what you'll see in the State of the Cryosphere report over and over again, there's no negotiating with the melting point of ice. These are essentially permanent, with the exception of Arctic sea ice, which can come back in decades, or maybe, it could take as long as a century, depending on how warm the oceans get. But in terms of glaciers and snow, 300, 500, maybe 1,000 years to restore a glacier. Ice sheets are an even longer time. We will get extreme sea level rise if we stay above 2 degrees C for any long period of time. Permafrost, once permafrost thaws, for new permafrost to form takes many, many centuries, if not thousands of years. And polar ocean acidification, in many ways, the longest, 50 to 70,000 years. But the level of risk and damage from cryosphere to the globe is really dependent on peak temperature. And it's really important to understand that. It's not good enough for the cryosphere if we go up and come down again. It will continue responding to whatever peak temperature was. Every 1/10 of a degree counts. At COP26, one of the things that a number of especially mountain countries with glaciers and snow are focusing on, but also those concerned by the cryosphere, there is a desire to bring cryosphere dynamics more explicitly into the negotiations, because this is really complex science. This is a gallop through the science. And when it's been addressed at past UNFCCC meetings, it's usually been one presentation of 10 to 15 minutes, if that, with maybe 5 to 10 minutes for questions. That's not enough time for policymakers to absorb this. So there's a real need to take the time. These are called dialogues. They're normally a full day, or you can do a workshop for maybe a half a day. But regardless, at COP25, when the COP accepted the special report on lands and the special report on oceans and cryosphere, there were dialogues mandated on lands and on oceans. The COP was entirely silent on cryosphere. And unfortunately, so far, this COP is too. So there's a need to consider these disparate elements and what their thresholds are. Arctic sea ice, the 1.7 degree threshold. Permafrost emissions, they're ongoing and increasing. There will come a point where there's very little permafrost, at least subsea, near surface permafrost left. Glacier snowpack related water resource loss is ongoing. As Heidi mentioned, we've already lost many tropical glaciers and mid-latitude glaciers, but the threshold there lies between 1 degree for most tropical glaciers. By about 2.5 degrees, almost all glaciers in the world are gone. And again, it takes a very long time for them to come back. Ice sheets and sea level rise, real threshold behavior between 1 and 2 degrees C. And ocean acidification, most I would say ocean acidification experts think that for the polar oceans, there's a real threshold right around 450, which is about 1.5 degree. So all of these are tied to CO2 emissions, tied to our carbon budget, tied to peak temperature, and that has clear implications for Paris Agreement and UNFCCC processes that are tied to temperature, like the second periodic review and the global stocktake. And so this science really needs to feed into that in a major way. And right now, there's no way to make that happen except by maybe references to AR6. But again, a real deep discussion of this has not taken place at any COP or at any bond meeting. Bonds are the intersessionals. And the cryosphere science community really believes that needs to happen so that parties have a better idea when they're doing the second periodic review of the long-term temperature goal, when they're doing the global stocktake aimed now at, we're already on our way to 2025, right? These need to be taken into account. And that's why there's a desire to have, as part of the COP26 cover decision, to mention cryosphere, because right now it isn't anywhere. The word does not appear in the cover text. And to ask for a cryosphere dialogue workshop, something much as has happened with oceans, but this is a little bit different. It's a narrower process to feed into these two things, the second periodic review and the global stocktake. Finally, to end with a bit of hope, we do have something called the 50 by 30 Coalition. It is those governments and also those scientific institutions that are really concerned about this and that currently have 50 by 30 consistent goals and actual measures to implement them. Very few countries do. Most of the Nordics, Germany, the UK, Scotland joined last week. So they have 1.5 consistent policies if they fully implement them. Now, I've got to say, this doesn't take equity into account, but all we're focused on right now is just the physical reality. And the reason we're doing this is to make it clear that this isn't impossible. Because sometimes there's a lot of defeatist talk, but there are governments that are taking the steps they need to. They need to do more, but the rest of the world needs to do even more. So you'll find the full report of the state of the cryosphere online. There's a QR code. Unfortunately, I think we're out of all our paper copies, but we're all here, Heidi, Julie, and I, to answer questions as we can. And so we'll open it up to questions on any of these dynamics, anything having to do with the role of cryosphere in COP26 and ongoing. So Heidi and Julie, if you want to come up here. Are there any questions? You'll have to come to the microphone.
Hi, I'm Roberta Benefield, and I'm with Grand River Keeper Labrador, from Labrador. We've been doing some research, and I understand that all of your presentation has been about what is happening. My question is why it's happening. Is it all about CO2, or could it be possible that some of these, like the ocean acidification and ocean temperature rise and melting ice sheets, could be due, and we have some documents that say that this is true, could it be due to all of these massive hydro dams in Russia and Canada and around that would be, produces more warm water than they should? And anyway, have you considered that in this whole process?
I don't know if you want to take that, Julie, but yes, actually, the IPCC has looked at other possible explanations, and it's CO2. It's fossil fuels.
These waters from mega dams, for instance.
I think Pam's right that the CO2 and the temperature, just like David Attenborough made it, it's one number that matters, and that is the big problem. The hydro dams probably have some small local effect. It's a good question. We've even thought about, there are people worrying about contributions of sea level rise from the extraction of groundwater, right? We extract groundwater, we use it, and then we send it to the ocean. How much is that? So there are things like that people are looking at. But at least right now, and I'm happy to take whatever information you have and share it out, but I don't know of anyone that's actually identified that. Even if it's 5%, it would be good to know what is that factor. So I don't want to dismiss what you're saying. I want to just say that I haven't heard that it's CO2 really is the big elephant in the room.
Elephant in the room as well. And I'd love to connect with all of you later and present some of the information we have. Thank you.
Thank you.
Hi, thank you for the presentation. It's Paul Beckwith. In all of your slides and all of your data, your baseline is 1880 to 1910, the average, right? All of them. And yet in some of the slides, you call that pre-industrial. Okay. The original definition of pre-industrial is 1750. The difference between the baseline you're using and pre-industrial in temperature is about 0.2 to 0.3 degrees Celsius. Okay, the original baseline, the IPCC and COPS and everybody used when those 1.5 and 2 degrees Celsius numbers came out was relative to 1750, relative to pre-industrial. Okay, so my concern is the baseline is shifting. What's to stop the world community saying, okay, we're going to use a baseline of 1950 to 1980 now, and we're well under 1.5 and everything's hunky-dory and fine. Like, you can't shift baselines without, whenever you report 1.5 or 2, please report the baseline. Come up with a name for the new baseline. Call it turn of the last century or something, but don't call it pre-industrial, because that's not correct.
Yeah. No, I appreciate your point. And it's also very true that depending on the data people are showing, they will use different windows of time to show that. So that's fair enough that we need to be better at maybe pointing that out. And I appreciate your precision. We do probably get sloppy. I tend to use like 1885. And as you're pointing out, well, that's too late. So yeah, your point's well taken. And I think it's true that depending on the data set, we tend to use different multi-decadal averages, say usually 3 decades at a time, windows that slide. And we don't want the real number to change. And I appreciate what you said.
I will say that it's sort of internally consistent in terms of how the IPCC defines it and defines the impacts. Though one of the things that I think is even more dangerous in terms of raising the same point that you're doing, Arctic sea ice, for example, the National Snow and Ice Data Center, which a lot of people use, they move their baseline all the time, and it makes the ice loss look less than what it actually is. But the weather services do the same thing, right? When we hit 2021, suddenly the average shifted and it made things look less warm than they actually are. So that's a bit of a creeping distinction that is potentially dangerous.
Hi, Phil Rafels of the Bolin Centre in Montreal. Just a clarification question, really. One of your slides that showed a 2 to 3 meter sea level increase at 1 degree. Now, my understanding is we're already past 1 degree. So does that mean that we've already had that 2 to 3 meters, or is it a question of a time lag? And there's that for every change so we haven't yet absorbed the sea level increase that flows from the current temperature. Could you explain that?
Yeah, that's very true. The ice sheets are slow beasts, and it's going to take a while for them to catch up. So what's happening to the ice sheets right now is in response to decades ago. And what's happening today is going to be they're responding in the future. There's this long lag time. And you're right on. It's going to take a while, but as it warms more rapidly, we expect that melt to increase more rapidly. And we know that the big factor coming out of Greenland right now is extremely rapid melt, and it's increasing. So yes, there is a lag, but we are baked in. It's baked in that we already have this pending sea level rise. We can slow it down, but it's going to happen. So yes, if I was, God, and I could turn off the CO2 everywhere for every, just let's go to net zero tomorrow, we're still going to have sea level rise. Oh, we're going to have sea level rise over millennia. It's going to keep going. So that's what we have. That's what we're facing.
But the point being that it's a lot easier to adapt to 2 to 3 meters over 2,000 years, than by 2100, which at high emissions, some of the outliers and some fairly well-respected entities like the Arctic Council have said 2 meters at high emissions by the end of the century. So that's going to be a lot harder to adapt to.
Set this up. I wonder if you could put the slide on that had the fossils on at all. I've got a little geological question. It follows on from the question the gentleman just asked. And the question is, can you see the time lag at all in any of the previous interglacials in sediments from around Greenland? And can you also see in those sediments from around Greenland any damage to the fossils? I mean, see the picture there with the evidence. I mean, Hutton said the present is the key to the past. And can you see damage to foraminifera, for example, in the sediments of the past, which would allow mapping of previous acidification events?
I've often asked that question of my colleagues who study these little guys. And, you really have to go back to get this kind of CO2. You really have to go back to the Pliocene. And, if we go back even 40 or 50 million years ago, there were these little guys with much higher CO2. The difference is that the span of time they have to buffer and to adapt makes a big difference. So what's happening now is so fast, these ecosystems do not have a chance to respond. I have heard that there are some coral reefs kind of figuring it out, how to deal with this in a warmer waters. But I think that's the big difference, is the scale and rate at which things are happening is more than these ecosystems can handle.
So you can't actually see any damage in the foraminifera from previous glaciations then?
No, we do not see that in previous, because you really have to go back, to 3 million years to get this type of CO2. And the only place in previous interglacials that we see this kind of corrosion is when we get into the very deep ocean waters where it's really cold and you're below it, gets below what's called the carbonate compensation depth. And so we know about that. That's kind of normal. But surface waters, this kind of corrosion is a Pliocene feature.
Hi, Chris Wilkie with Waterkeeper Alliance, and I found some of the most chilling slides you had. Well, besides the sea level rise and the dire predictions all around, but talking about very important species like the cod getting squeezed from the north to the south. And where I come from, in the west coast of the U.S., salmon are very important, and we're already seeing declines in those. And I'm just wondering how this information is being communicated with the biologists, the marine biologists that are figuring out the ecosystem dynamics, and where would we go to look for those types of long-term predictions over hundreds of years? Because most of the stuff I see on an ecosystem level is typically very short time frame.
I mean, it's part of what we're trying to do here, because a lot of, like, marine biologists, for example, they're focused more on very near term. Same thing on sea level rise. There's a bit of a debate, an interesting debate, where I live in southern Sweden, which is the lowest lying point in Sweden. It's below sea level, and the town of Kristianstad is trying to figure out how to deal with that. How, they've already got 7-meter levees, preparing for the future, and they've had some studies done by consultants that have told them that's enough, and there's a researcher down at Lund University that's saying it isn't enough. More of that needs to take place so that more realistic judgments can be made. And here again, that's why we're trying to bring it here into the negotiations as well. But I would say it probably hasn't filtered down to the local level the way it should.
Yeah.
Maybe where you are.
Yeah.
Yeah.
I think you're spot on that we have a lot to learn about this, and particularly like in the Yukon-Kuskokwim Delta of Alaska this year, it just wasn't any salmon. A lot of fisheries the fish didn't come back. And they're moving north. Some of the pelagic species are moving north into waters where we don't have regulations. And so there's a moratorium now about Arctic fishing until we get the regulations figured out. But you're right. I think that the fishing and science and biologists are rapidly learning about what's going on and monitoring that. So I think it's a good point. It's unfortunately an emerging science that we're beginning to observe because of the collapse of some of these rivers, the spawning systems that have gone on in many coastal areas, from Washington State all the way up through the Bering Straits. There's an impact.
A quick question, just a confirmation. So you were describing many processes that were irreversible if we zeroed emissions, right? If we deploy solar radiation management, none of these things are irreversible. Do you want to confirm that? So we actively cool the planet, like, for example, Stephen Salter's marine cloud brightening, or sulfur in the stratosphere, or things like that. Like, a large volcano goes off, the Earth is cooled for 3 to 5 years. If we continue that process with solar radiation management, these processes are all reversible.
That's actually not the case. Again, these processes are tied to peak temperature, number one. Number two, I'd encourage you to watch the 230 event that was focused on solar radiation management. One of these processes, ocean acidification, would continue, right? Because you're still pouring CO2 into the atmosphere. So that's number one. Because you're continuing to raise CO, or you're saying you go to net zero and deploy solar radiation management?
This is a different process. Solar radiation.
No, I know what solar radiation management is.
Okay,
so if you deploy it,
right,
correct?
And we deploy CDR as well.
We don't have CDR at that scale right now, sir. We just don't have it. The only way to do it is emissions reductions.
We can stimulate plankton growth in the ocean.
That's been attempted. It isn't going to work at scale. Unfortunately, this is why emissions reductions are such a thing. But the other reason I think it's important for people to look at that particular side event is the side effects of deploying, especially sulfates, but any brightening technologies. Think about it, right? When you are stopping sunlight from coming in as opposed to stopping heat from going out, that affects the climate system in a very different way. And at the same time as you do have a cooling effect from volcanic eruptions, you're also getting famines throughout the northern hemisphere because sunlight is blocked. So plants can't mature, the crops fail, number one. Number two, precipitation really gets perturbed. The Indian monsoon fails. Okay, so there are, and if you're deploying this technology and then for some reason you have to stop it, then you get a real rebound effect, which occurs much, much faster than the Earth can. So I'd rather not get into, you've got people behind you.
I just want to say that you can't make these statements because almost no money is being put into SRM technologies and CDR, carbon dioxide removal technologies, right? Scientists are not studying this.
Actually, they are.
It's-
They are. They're very well funded. Yeah.
There are so many scary slides to pick in the scary presentation. So I'll gonna pick the slide about the permafrost and carbon budget. So if you could bring that up again, because I was wondering. I think you had basically the carbon budget reduced by the emissions from the permafrost till the year 2100. But in some way, basically, I think you are, or we're facing that we are installing kind of eternal costs also, because these emissions, they will still keep going also after the year 2100. So it's a bit of a question, even if we can basically reach net zero with everything else, this kind of would mean that we would face a need for negative emissions for basically forever, just to compensate
a couple
the
hundred
permafrost
years,
part, or how
between
would you
about
say?
100 and 200 years, and then all the carbon is out of the permafrost. So, but it's still, see, this shows that difference, right, between 2100 on the left and multi-century, which is about 150, 200 years. It's a little uncertain, but it does eventually cease because there's no more carbon left to emit in the soil.
Not sure if I'm really glad with the answer, but thanks.
Yeah. Let me just add that there was a really interesting synthesis paper that came out from the permafrost community that still made the point that yes, there is all the methane and CO2 coming from permafrost, but the biggest emitter is us. So they still emphasize that we have to decrease our emissions to slow it down, and that we still need to be concerned about permafrost, but they still make that point about what's happening. So I can, if you want to give me your email, I'll send you that paper, because it was kind of an interesting find.
Just a very brief question afterwards. Is there a massive difference if we face an overshoot scenario compared to a direct reduction in that terms?
Because it's again, it's determined by how far the overshoot goes. Again, once permafrost thaws once, it continues. It's the gift that keeps on giving. And so the only way to prevent it is to stop it from thawing in the first place. So that's, but again, unfortunately, you can get, a single extreme weather event and you'll get more thaw. So we just have to keep temperatures down as far as we can.
Let me just remind you that the permafrost is there because of the cold glacial cycles. So it's going to be very hard you can't build it back. It's 300 to 400 meters thick in places because of repeated glaciations over long periods of time. So that's part of the problem.
Any more questions? Yeah.
I've got a layman's question. I'm a journalist, not a scientist. It's pretty scary, but apparently big portions of societies around the world just don't know about it. So is there any cooperation between you, the science community, and I don't know, the filmmakers, not documentary makers, but in the sense, I'm not sure, are you old enough to see that movie, The Day After Tomorrow, after nuclear sort of Armageddon, or there is a film called The Flood, when London, the barriers fail and London is flooded. Any cooperation to get it into the minds of the millions of people?
Some of these movies are very Hollywood, like The Day After Tomorrow. I've actually used that film in classes, and we go through the first 15 or 20 minutes of the film, and there are events in there that, they're real. That's what's happening. And then, of course, it goes to Hollywood. What I would rather, I think there are a lot of really good filmmakers out there communicating, like Kurt Johnson through Nova made a nice, it's available and through the Nova programming on the polar extremes, talking about both poles and the history of that. And I know that's been widely seen. There are a number of really good films, but I think it's so important for all of us, scientists, anyone alike, to really communicate these. And also, I think we all share the idea that this has to be a hopeful story. There has to be, we can do this. We have to just take it on and really think about the economic positives and all of that can come of this, because it cannot be gloom and doom. If we do business as usual, we're going to just have big issues to deal with, and we're going to have to take those on. So it's a matter of, we have to be optimistic, because, well, being pessimistic is no fun. But we really have to think positive and get on it and tackle it, and communicate it to the public in a way that they don't feel helpless. Because if someone feels helpless, then they just throw up their hands, and that's not what we need. We need everyone to dig in. This is all hands on deck.
And I think that's a really good note to end on, that, again, this is not inevitable. We really can prevent these things from happening through emissions reductions. But the difficulty is communicating that this is just as urgent as COVID, even though we're not going to see the results as quickly. And I think that's the task before the scientific community and before the journalistic community also. How to communicate that so that people understand that it's not just a matter of ambition, it's a matter of urgency over these next 10 years. So thank you so much. Welcome back here tomorrow. We'll have at least a few side events, including, I would say also, we have 4 very excellent early career scientists who've been volunteering at the pavilion all week. They will present their work, and there will also be an analysis of 50 by 30 countries at 10 a.m. that goes into how countries can do it. The countries that are consistent with 1.5 degrees, what does that look like? So you're welcome back tomorrow, and I think we're all waiting for the next version of the cover text. Thank you so much.